Okay. Hello, everyone. My name is Jess Nessery. I'm an associate professor here at Rice University. Welcome to the International Methods Colloquium. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Rice University and the National Science Foundation. This week's speaker is Casey Crisman-Cox from Washington University in St. Louis. His talk is entitled Estimating Signaling Games in International Relations, Problems and Solutions, and this is co-authored work with Michael Gibalisco at Caltech. Casey's talk will last between 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of the webinar window. You may ask questions at any time during the talk, but all questions will be held until the end of the presentation. A link to Casey's paper and slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I will post those links right after we get finished with this introduction. And now I'd like to welcome Casey Crisman-Cox to the IMC. Casey, welcome.
Thank you, Justin. As we said, this is a paper today I'm going to be talking about estimating signaling games in international relations, the problems that applied researchers face in doing so, and some solutions that we have to make this process better. So let me just start by describing a little bit what the where crisis bargaining fits within the international relations literature. So the model, like the one you see on the right, is essentially the standard kind of workhorse game theory model for international politics. And it's been used very frequently by applied formal modelers and EITM scholars over the last decade or so to study topics as diverse as audience costs, the initiation of sanctions threats, how disputes escalate from peace to war. And during this period, there's been many attempts to fit this model to data. And what we're setting out here to do is to make this process both easier and better for the analyst. And so in fitting this model to data, analysts tend to face two major hurdles. The first is how to handle the fact that this underlying crisis signaling game can emit multiple equilibria. This problem was first identified by Joe in 2011. And since then, work has sort of continued in this vein, with most analysts continuing to apply a method that goes back to Signorino 99 that is appropriate only when the game has a unique equilibrium. And so the issue as to how to face this multiplicity problem is very much an open question in this literature. The other side of the applied researcher's dilemma here is this worth the computational expense of fitting this model to data? And there's some papers here, all of whom actually kind of mention this in their discussion and decide to instead adopt a reduced form analysis rather than a structural approach that would directly account for this game's strategic dynamics. And in those cases, it very much seems to be the case that analysts just want to avoid the fact that this model is difficult to fit to data. It's a involved process. And we also are very much interested in making that process easier. And so to that extent, we're contributing to the applied research on signaling interactions in a few different ways. So first, what we're going to do is adapt some dynamic games estimators from the econometrics literature and pare them down and apply them to this IR crisis signaling game. And we're going to analyze how these different estimators perform in a variety of Monte Carlo and practical applications to see if they can improve upon existing methods. And then at the end of all of that, we can offer some recommendations for how best to go about analyzing signaling interactions, and also we also introduce some easy to use R code that takes the basic computation time for this problem way down, making it much, much more feasible for applied researchers. And just to preview some of our results, as I was saying, in all of the experimental settings that we consider, our proposed solutions are both, perform both statistically better and are computationally much faster than current best practices. And this is going to be true even in the sort of the ideal case for current best practices, which is when a unique equilibrium is generating the data. And we're going to talk more about what that means more precisely as going forward. We're also going to show that some pseudo-likelihood based methods are going to be sort of the best approach in terms of both performance, statistically, and in terms of time to fit the model. And finally, we are going to conclude in our application that current best practices can be misleading in some examples. Specifically, we're going to show that it underestimates the role of audience costs in the decision to initiate and economic sanctions disputes. And our solution is going to remedy all of these problems. So before we get into that, it's worth taking some time to describe what the sort of underlying model is. And so this, as I mentioned before, is kind of a workhorse standard model for international relations scholars. And just to walk through it real quickly, we're going to have two actors, a player A and player B. And player A is deciding whether or not to issue some kind of threat or challenge to its opponent, or to just accept the status quo. If he chooses not to challenge, the status quo is retained. If he chooses to challenge, then B has the option of either resisting this challenge or giving in and conceding to A. If B resists, then A has to decide whether or not to follow through on its threat and actually fight with B, in which case we end up in this stand firm node where players receive their war payoffs, or A can back down, in which case it pays some kind of an audience cost, and B gets a victory payoff for successfully resisting. And so there's going to be some information in this game. So each side is going to have some form of private information about these payoffs. Specifically, both sides have some private information about the costs or benefits to war. That's going to be epsilon capital A and epsilon capital B for each player. And A is going to have some additional private information about what its audience costs are, or how much it pays for backing down, which is going to be denoted with epsilon little a. And for purposes and for ease of exposition, we're just going to focus today on the case where all of these shocks are IID standard normal. There have been many generalizations of this model proposed over the years, which make this information structure more intricate and complicated. But today we're just going to focus on this easiest example. And so when we talk about an equilibrium to this game, we're going to be focused on Equilibria has choice probabilities the same way that McElvey and Palfrey and Signorino focus on. And in this case, a strategy is going to be a set of three choice probabilities. So PC is the probability that A initiates a challenge. PR is the probability that player B resists that challenge. And then PF is the probability that player A follows through on that challenge, conditional on having made it. So the probability of fighting, conditional on challenging. And we're interested then in estimating what these payoffs are for each player. And so our structural parameters theta are going to be the payoffs for each actor. So the audience cost, the cost that B pays for backing down, the status quo payoffs, the victory payoffs, and the war payoffs for each player. And as is well known in this game from Joe 2011, an equilibrium is going to exist, and it's going to be a solution to a system of smooth equations. So P tilde here is an equilibrium if it solves this system of equations, where here all we're looking at is just a series of best response functions. So G and H are player A's best response functions given B's probability of resisting. and F is B's best response to A's probability of following through with the threat. And so with that sort of quick basic setup in mind, we can start to think about how analysts have been going about fitting this to data. And so the data in this setup is going to be a series of D games, or in this case, dyads, since every observation is going to have an A and a B actor. And then from each dyad D, we're going to observe some number of observations T, where all of the observations for dyad D are generated from an equilibrium P star, and some covariance X D for that dyad. So, I mean, just so we're clear about this, P star here is going to be dyad D's data generating equilibrium. It solves the equations that we just looked at. And for the purposes of estimation, we're going to need to parameterize our payoffs, where each payoff for each actor is just going to be an X beta combination for that particular dyad. And then our goal here is for all structural enterprises is to back out what these payoff parameters are. And so, since we're dealing with just a standard kind of multinomial choice model, the best practices to this have been to follow standard multinomial choice modeling. So going back to Signorino, and if you want to go even further back into the econometrics literature, into Rust, we see that the standard approach here is to use a likelihood, which is just the log probability of observing that outcome summed up over all of the observed outcomes. Where what we see is that if we observe a status quo, it's just 1 minus the probability of challenging. We observe a concession from player B, is the challenge minus the resistance probability, and so on for the remaining outcomes. Where these choice probabilities come from, though, is going to be where this gets a little more intricate. So in this setup, we take a guess at the parameters beta, compute an equilibrium using some kind of nonlinear equation solver, and then use that to compute our choice probabilities, which we then use to evaluate the log likelihood. And if we're dealing in the situation where there is only one solution to the system of equations, then everything is fine. But where we're going to run into trouble here is the fact that, as we mentioned earlier, this system of equations might have multiple solutions. And so let's just take a moment here to talk about where that might start to break down this process. So under some conditions, we can see that this is sort of like the ideal case. There is a unique data generating equilibrium where for every value of the regressor, we have a single equilibrium in the data that is producing the outcomes. And this is great. This is exactly what we would hope to find, and this is sort of ideal for applied researchers. The problem, though, is that if we just tweak these a little bit, in this case, all we do is make war just a little bit worse for both actors, we can find that there are multiple equilibria associated with the data and the parameters. And so this is going to be perhaps somewhat troubling here, where if we, for any given guess of the parameters, we don't know what our nonlinear equation solver is going to return. And it may or may not be the correct equilibria for the data generating process. And just to put a slightly finer point on that, we can describe sort of how this kind of jumps the tracks from standard forms of discrete choice modeling, where we start with a single input or guess at the parameters. We can have then a single probability that comes back from that. So if we think about a standard probit case, we take a guess at the parameters. We have a single probability that comes back from that. We have a nice log likelihood that returns from there. Where the multiplicity from the previous slide is going to be troubling for us is that, again, while we start with a single input or guess at the parameters, we end up with multiple candidates for what choice probabilities are associated with that guess at the parameters. And from there, we end up with 3 completely different log likelihoods, all of which are from the same guess at the parameters. The likelihood function is really not actually a function anymore, because for a given input, we could have 3, 5, 7, however many possible outputs. And so this is going to raise a couple questions for how we would want to go about this. So specifically, we want to know, how do we choose amongst those possible equilibria? Can we do that without actually taking the time to compute all the possible equilibria that might be associated with a given set of parameters? And is there a way that we can start to refine a way or eliminate these a priori so that we don't need to worry about them in the estimation section? Can we save ourselves some time up front? And by and large, this has led to sort of 2 proposals for how people deal with this in the literature, so they can continue to use the standard tools that we just discussed. The first kind of basic proposal is to just kind of hope that there is a unique equilibrium in your data generating process. And then if that's true, analysts argue, then everything should work just fine, because we will always get the right choice probability. There's only one candidate solution. However, it's not going to be quite so easy there, because it's going to turn out that this approach will sort of only work if you give it very good starting values. Starting values are very close to the truth. And if you can't do that because, well, you don't know that, or you don't know what the truth is, then at some point in the optimization procedure, there's a good chance that the likelihood will be evaluated at some set of parameters that, where multiple equilibria exist. And that's going to lead us right back to this problem of not knowing which output to use, and then we might end up following the optimizer into very troubling territory. The other sort of candidate solution that is going to come out of this is to, as I mentioned before, try and refine it away. Maybe we can use something like divinity or the intuitive criterion to just get rid of these multiplicities, and then we don't need to worry about it anymore. This is also not going to be something we can rely on in this game. For one thing, we're going to show that, or we do show that almost all equilibria in this model are going to be regular, which is a very strong refinement that's going to imply and subsume all of these sort of other standard refinements that we might rely on to eliminate the multiplicity problem. So in that sense, we're out of luck. And so with those sort of standard approaches no longer available to us, we might be tempted to find some ad hoc criteria that can winnow away the possible equilibria. But this is also going to be troubling for us, because we're still going to now have to be in a situation where we need to compute every equilibria for every dyad, every observation, and then find the one that meets our criteria, and then use that to form our likelihood. And that's going to be exhausting for us on a couple different fronts. The first is that we have to compute all those equilibria, which is going to be time consuming. And then the second part is that this is going to introduce discontinuities into the likelihood, because we're going to be bouncing from places where our candidate equilibria or our criteria exists, and then to places where there's just a unique equilibria, and then back. And as we put in more observations, this is actually going to introduce more discontinuities for whatever criteria we end up using. And just to give you a sense as to how expensive this is computationally. In our applied example that we're going to look at later, we try doing this just to see how it works. And this optimization, which is that particular optimization, is currently in its second week of running with no end in sight. And so it's just not really feasible for analysts to go down this approach because it's just so demanding on our resources. And so with both of those avenues closed off to us, this problem might seem a little bit out of reach, but that's where we come in. And what we're going to do here is we're going to adapt some approaches from the industrial organization and marketing econometrics literature, and then use those to accommodate the fact and directly model the fact that these games have multiple equilibria. So by including that directly into the estimation procedure, we can save ourselves both time and resources there, because these approaches are going to be much faster than everything we've described so far. But they're also going to be much better performing because they explicitly account for the fact that the underlying game can have multiple equilibria. So the first approach that we're going to look at here is going to be a pseudo-likelihood approach. And it's going to be a two-step estimator based on some work by Hotz and Miller in the early 90s, where the approach is to first find some consistent estimates of these equilibrium choice probabilities. And then using those, we can evaluate the log likelihood by fixing our first stage estimates and then evaluating best responses to those and whatever our given our current guess at the structural parameters beta are. And then this estimator will maximize the pseudo log likelihood for this fixed and first stage estimates, for these fixed first stage estimates. And this will give us a pretty feasible approximation of what the true maximum likelihood estimator would be under the correct equilibrium selection, so long as these first stage estimates are good. And the question then, of course, is, how would one go about obtaining good first stage estimates? And sort of approaches that we have found to work pretty well are a random forest, just using a set of predictors in that, or if you have large enough within game observations, just frequency estimators will be perfectly consistent. But again, this approach tends to rely on getting these first stage estimates right. So we might be interested in an extension to this that will relax that reliance on the first stage estimates. And then we can do that by just iterating it. And this is an extension that's been proposed to the pseudo-likelihood in the past, where we start with the pseudo-likelihood estimates of both beta and those first stage probabilities. And then we just iterate between updating the choice probabilities using the current estimates of beta, and then using the updated choice probabilities to compute a new beta. And we just do that over and over and over again until we get convergence across all three of those parameter vectors. And this is going to be nice in the sense that it reduces our reliance on the first stage estimates, and it is still reasonably fast. In practice, we find that this converges in usually under a minute in many data examples that we've tried. And so those are two pseudo-likelihood approaches, and they both work very well, as we'll see in a moment. But we might also be interested in something that is a little bit more refined in the sense of being closer to the true maximum likelihood estimate. And so that's where this constrained maximum likelihood estimator is going to come into play. And so what's nice about this is it's going to treat the equilibrium parameter of interest, PR, the probability that player B resists, has a parameter to be estimated and a nice full information setup. So we're no longer doing a two-step or a k-step procedure here. So now we have the same log likelihood function that we considered at the very beginning. It's just the same multinomial log likelihood function, but now the choice probability is not being directly computed from the parameters. Instead, it's being treated as a parameter itself, but we force it to be in equilibrium with the data and the current guess at the parameters. So this is now a constrained optimization problem where we maximize the same multinomial log likelihood while enforcing equilibrium play. And this is going to be equivalent to the maximum likelihood estimator that would always select the equilibrium for each observation that maximizes the total log, maximizes that observation's log likelihood. And so this imposes a selection rule in the sense that it is choosing the equilibrium that maximizes the likelihood, but avoids computing each equilibrium for each observation and avoids the discontinuities associated with that. And so we're saving ourselves a pretty massive computational burden on both those dimensions, while introducing just sort of one caveat here, which is the fact that we're including some additional parameters, all these PRs, which means that this estimator will only be consistent as the number of within-game observations increases. And so we've got now a current best approach and 3 candidates for improving upon that. So we're going to be interested then in how these things perform in a variety of settings. And so the first thing that we're going to look at is how it performs in a situation where the data generating process is has multiple equilibria. So in this case, the data are being generated from the parameters that we saw before, where each underlying game has the possibility for multiple equilibria, and equilibria selection then is determined from the observable regressor X. And so what we're seeing here is the logged root mean squared error averaged over all the structural parameters in a variety of settings. So within each pane here, we see the number of dyads that we're observing. And then on the x-axis here, the number of observations that we observe each dyad. So we can think about this as sort of dyad year data, if you want, where we have in this first top left panel, 25 dyads observed for 5 periods, 25 periods, and so on. And what we can see here is that the traditional maximum likelihood estimator in all 4 panels in this kind of light blue is always the worst performing and generally doesn't get any better as either D or T increases. Additionally, we can see some of the concerns of incidental parameters that we talked about before, where the CMLE is still doing better than current approaches, but is getting perhaps a little bit worse as the number of incidental parameters increases. And so where we really want to keep our focus then is on these 2 pseudo-likelihood approaches. So we have the 2-step pseudo-likelihood in the solid green line is doing consistently well across the board, while the iterated approach is, with this one exception up here, almost always our best performing estimator in any of the experimental settings that we've looked at, that we look at here. And so this is a case where sort of current best practices you might think are set up to fail, and you might be interested in how it does in sort of the best case scenario for best practices, which is when the data generating equilibria is unique. And so looking at the Monte Carlo evidence there, we see again pretty much the same story. The current best practices is doing consistently just the worst across all the experimental settings. It's not getting any better as we add more data to the problem. Whereas our other three estimators are all doing really pretty well. There's no sense that these are having any trouble at uncovering the correct parameters. And so just to recap here, the sort of standard or traditional maximum likelihood approach that is ignoring the multiplicity is going to perform the worst in all of these settings, whereas our pseudo-likelihood and our the iterated version of it, the nested pseudo-likelihood, are our best performing options. And across both sets of conditions here, the performance is largely the same. And so we have pretty good confidence that our approaches can do very well in both types of settings here. And so with that in mind, we're going to take a moment to talk about how this works in a real life application. And so we're going to focus on an application that looks at the threat to implement sanctions against a country. And this is going to be similar to an AJPS article by Wang and others in 2015 that looks at kind of the same question using the same data and the same kind of basic approach of fitting a signaling model to this data. And so we're going to be looking at data from the threat and implications of sanctions data, known as the TIES data, where we have whether or not a country initiates a sanction threat against another country, whether or not that country backs down or gives into player A's demands, and if player A or if player B doesn't give into the demands, then player A has the choice of either actually imposing sanctions or backing down from the threat. And so we're going to look at this interaction over 418 politically relevant dyads, very much in the same way that Wang et al. Do. And within each dyad, we're going to observe 120 plays of the game by looking at the sort of dyad decade has our overall unit of analysis and then monthly level interactions within that. And so we specify this by looking at the following. So for the status quo for player A, we include the economic dependence that A has on player B, player A's polity score, and whether or not the states are contiguous. Player B's status quo is fixed to 0. For the situation where A makes a threat and B backs down, A receives receives a constant term plus whatever A's expected costs were to going through with the threat, and whether or not the countries are an ally or allied. In player B's utility here for backing down, we have a constant term, B's economic dependence on A, the expected costs to B if the threat had gone through, whether or not the countries are contiguous, and whether or not they're allies. In the situation where we have B resisting and A following through with the threat, we have for player A actually following through, a constant term, A's economic dependence on B, A's polity score, and then the capability ratio of the two countries. For B, if it finds itself being sanctioned, we have its a constant term for it, its polity score, and its capability ratio. And finally, in cases where A backs down, we have this audience cost parameter for A for making a threat and not following through. It gets a constant term and its polity score there. And then finally, for B, player B in this case, we have this fixed to 0. And so with all of that, we can going to focus our attention on this payoff for backing down for player B and for player A's payoff when it backs down. And so what we can see here is the results from these 4 different models. So we have the standard approach in the first column, and then R3 approaches after that. And then the primary thing I want to point out here is that R3 approaches, by and large, agree with each other, especially these last two approaches. So the nested pseudo-likelihood and the constrained at maximum likelihood, very much in agreement with each other as to what these estimates look like. Pseudo-likelihood also, by and large, agrees with that, while the standard traditional method that ignores the possibility of a multiplicity is sort of finding things that are in the opposite direction from the others, and sometimes in the opposite direction and significant in directions that are disagree with the models that we would prefer given the Monte Carlo evidence and what we know about them. Finally, what is interesting to point out here is going to be the situation of audience cost and economic disputes here, where the standard methods find really no evidence of any kind of audience cost for player A in terms of making threats and then backing down, whereas all the other three approaches find a reasonably sized and statistically significant audience cost effect on backing down from threats to sanction an opponent. And let's take a few moments to sort of talk about what these things look like. So in this case of audience cost, this point 3 here, we have the situation where in all three of our models, we reject the null hypothesis that audience costs are either positive or don't exist for every single dyad at P, in this case, adjusted for the fact that we're doing multiple comparisons. So even at the more conservative cutoff for P, we still reject it in every single dyad that audience costs don't exist. Whereas for the standard traditional method, we can't reject that null in any dyad, even at a lower standard. And so in this case, we find sort of true divergence here on an important substantive issue for international relations scholar, which is whether or not you actually are punished when you back down from a threat. And in this case, following the sort of traditional standard methods would lead you to the wrong answer on that question, whereas our methods all agree that, yes, the audience costs are a real thing in this context. Additionally, as an assurance to ourselves that our overall estimates make sense, we find that every single dyad that we look at meets a definition called competitive from Lewis and Schultz, which just means that these games are sort of interesting in the sense that victories are better for actors and backing down and concessions are worse for actors, whereas the traditional methods can't even doesn't even uncover parameters that meet this sort of most basic face validity kind of concern in these games. And just to continue a little bit on this audience cost situation, I want to talk a little bit about some comparative statics results where we can see that audience costs here are we find a nice kind of interesting effect on whether or not, in this case, the United States issues some kind of threat against China regarding economic sanctions in some way, where we see that at the United States' estimated value, sanctions threats are pretty low, but if audience costs were to either increase or decrease for the United States, we would expect more threats. On the one side, we would think that as leaders become less constrained, they make more threats because there's no real penalty for them if they end up backing down, which is sort of fits standard audience cost logic. But on the other side, we see that as the United States gets higher audience costs and pays more in cases where it backs down, it still threatens more, even though it might end up paying those costs later because its threats are now more credible. It can say, look, I have these high audience costs. I really can't afford to back down. So you better do what, you better just give in to me on this because otherwise we're going to end up in a trade war. And so in this sense, we have this kind of two effects of audience costs that go in sort of interesting and competing dimensions. And this credibility enhancement fits very neatly with some work on interstate conflict and audience costs that is that Mike and I have also done and is now forthcoming at the AJPS. We can also consider then how audience costs then affect observed outcomes. And here is where we really do see this credibility enhancement, where the United States, even though it doesn't want to pay these audience costs, so it makes threats and follows through with them when their audience costs are high. Whereas on the other side, as leaders become less constrained in the United States, they would make more threats and not follow through with them. And so this is perhaps going to be interesting in the age of Trump, where we might think more or less of him as more or less constrained than other presidents by his domestic audience, and whether or not that leads him to actually follow through on threats. But just to give us, just kind of wrap up here with some kind of general results then about how audience costs appear in the data writ large here, we find that in 97% of our dyads, more negative audience costs are going to increase the likelihood of threat initiation for this basic reason that threats are now more credible. And by and large, we also see that a doubling in a country's audience costs is on average going to be associated with something where between something like an 8 percentage point increase in the likelihood of a threat, just based on some linear interpolation. And so where we want to wrap up then is with just some basic suggestions for future scholars interested in this kind of work, which is that if you're going to go down this road, we would recommend you start with the pseudo-likelihood estimator. It's incredibly fast and works pretty well, as we saw. And then use those as starting values for either the iterated version or as starting values for the constrained maximum likelihood approach. If these approaches then work, you should have good reason to prefer them. You should go with those. Otherwise, there's nothing wrong with the pseudo-likelihood estimators. Estimates. They're consistent. They have nice properties, and they work pretty well. They're fast. While the major takeaway from all of this should just be avoid the standard existing methods for this, because we can do better on both a statistical and a computational front. And so where we're going to go from here is we of course are interested in expanding everything to include more general error structures that I referred to earlier. And additionally, we're working right now on an R package for both the pseudo and the iterated version of the pseudo likelihood, so that fast, reliable options for this model can exist and will be readily available. And then finally, we're also kind of interested in considering even more general estimators that will allow for more broad equilibrium selection rules than our current approaches allow for. So with that, thank you.
Okay. Thank you, Casey, for that presentation. At this point, Casey Crisman-Cox is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And I have a couple of questions. So first of all, I was looking at your paper as you were giving the talk. So usually when you think about there existing multiple equilibria in an extensive form game, it's because there's an unknown, there's basically a hidden parameter, right? There's a private information parameter that one state doesn't know the value of, and so the essentially the priors on that parameter strongly determine behavior, right? Because that determines how certain updates happen, and that ultimately results in different outcomes, right? If you think of like the beer quiche game, essentially the different equilibria are related to how people are going to either update off an equilibrium path or potentially what priors they might have. So looking at your crisis signaling game and sort of paging through your paper, what's the source of the multiple equilibria here? Is this some sort of hidden parameter or private information parameter or what?
Yeah, I mean, so the private information in this game is I referred to earlier is going to come into the form of these normal shocks, which are known to the actors in the game, but are of course unknown to us and to observers. And while each actor knows its shock, it doesn't know its opponent's shock. And so this private information then is going to be what allows actors to sort of have is going to induce the possibility of multiple equilibria, as you described, because it's going to be sort of based on, how kind of likely it is that A is fighting at that final node. And so based on sort of what the actors are thinking is going to go on there is going to determine sort of whether or not B is willing to resist and how B updates from seeing the initial challenge in the first place. And so when we see that situation where there are multiple equilibria, it's usually something along the lines of either A challenges a lot or a little, or some middle amount, and then B is doing the opposite of that. So when A is challenging a lot, B tends to be not engaging, but under the same set of parameters, we could also have a situation where A is challenging a little and B is resisting a lot, and that's just going to be coming from the fact that they don't know each other's shocks for war at the end.
Well, so is the distribution of epsilon is known to all the actors?
Yeah.
Well, if the distribution of epsilon is known, doesn't that cause a sort of convergence of priors and thus sort of force all the action down a single path?
I have to think more about that per se, but it doesn't seem to be doing it just because of the I would have to get back to you on some of that, just because I'm not entirely sure what the best answer to that question is.
Well, I mean, that's the prior end of things, right? You can have these weird prior beliefs that then sort of cause different things to happen because essentially the priors are different. There's also the potential for weird off-path beliefs, right? So think of. Go ahead.
Yeah, so I mean, nothing is going to be off-path in this game because there's every outcome is reached with positive probability because these shocks have support over the entire real line.
Right, and that was kind of where I was going. I'm wondering if there's that's the other way you can get that is another way you can get multiple equilibria, right? You have basically weird off-path beliefs that sustain some sort of equilibrium. What I'm trying to get my head around is intuitively. So I understand for sure that audience cost is a hidden parameter, essentially based on the state's mutual beliefs about those things and potentially what they believe about sort of what is going to happen later. If those beliefs are not updated according to Bayes' rule, that can cause sort of different things to happen, right? Anytime you get any kind of freedom in the belief space, you can get different equilibria. I'm just not, maybe it's been too long since I've really thought about this game, but what I'm trying to do is I'm trying to understand the source of the multiple equilibria in your model, right? So in other words, what you're saying is there are multiple probabilities, basically multiple action probabilities, multiple utilities that are associated with each pattern of outcomes, right? Because that's how this would have to happen, right? You have to have the same data, and you'd have to have multiple different strategy think that were consistent with that same data outcome. Is that right, or is that not?
Yeah, that part is right. So I think maybe the best way to think about this is in terms of how does B interpret A's threat, and in that case, B is thinking that in some equilibria, B will interpret A's threat. So where B will think that only sort of high types we can think of, or people whose error or shock for war is pretty low. So I think that only those types can threaten. But in the other equilibria, then we would also think that these are situations where the weak type or weak types also threaten. So in that sense, it is kind of similar to a Beer-Keech setup where you can have some kind of pooling in some sense where actors are, or all types, most types of actors are threatening, where in other senses there's going to be a sense where the signal is sometimes informative, but it's not going to depend necessarily. It's not going to depend on off-path beliefs because there is no off-path in this context. Does that clarify?
So what you're arguing is they're going to basically be in this game. They're going to be pooling and separating equilibria, or maybe semi-separating equilibria that exists for the same, essentially for the same objective utility parameters, right? And you can get either one happening. Is that right?
That's right.
But those are going to be quite different in terms of I would think they're going to be quite different in terms of behavior, right? So in other words, the outcomes of those games will be different. And
that's right.
So you're arguing that essentially it's the case that the previous ways of trying to deal with these models are not going to be able to, I guess, how would I put this? They're going to shift the utility parameters instead of shifting the equilibrium space. Is that right? Like they're going to basically try to find betas that are consistent with some other equilibrium.
That's right. That's exactly right. So, I mean, you got that exactly right. Where the sort of traditional methods will find betas that are consistent with sort of either one, and it doesn't know how to distinguish them at that point. And that's why we can use data in our first stage estimates to select or to find equilibrium, because it doesn't affect the observed outcomes. We're in essence, we're using the additional information that provides that you said.
So is there, usually I think the way this is, one way this has worked in the past is you try to, let me ask it this way. So in the Signorino papers, you essentially treat those errors as, there are several ways you can treat them, but the easiest way to do it is to treat them as sort of pure noise, right? They're simply noise factors, and you get a unique solution from that model, right? If in essence, you can say, well, contingent on knowing what epsilon was, you would have a unique solution to the game, right? So in other words, if epsilon was common knowledge, if it was known to the actors but not to the analyst, then there would be a unique solution to the game, and then you could essentially predicate your estimator on that.
I'm not sure I understand what you're saying there. So what it sounds like what you're saying is that if everyone knew, if this was a perfect information game in the playing of it,
right,
then we would have a unique.
But the analyst didn't know, right? So it was hidden information from the researcher, but it was not hidden information to the players.
Yeah. Yeah, I mean, that would be a kind of, so first of all, that would be a pretty different setup, right? So in that case, there wouldn't really be any signaling going on between the actors because they would know.
Right.
But yeah, that would be one way to eliminate the multiplicity. It would be to remove private information. But in that case, then I think we kind of lose the major advantages of this model from a.
Is there any way to recover, to use this as a measurement model? In other words, to recover information about for example, in panel data set, you're going to have multiple observations of US or multiple observations of China interacting with multiple different dyadic partners because you have dyad level data.
Yeah.
Is it possible to use your model to recover estimates of of the private information parameters, and then sort of basically say, I can estimate the audience cost associated with crisis bargaining with these states, essentially because your model is identifying one of the equilibria as being the best one, and that's predicated on a certain value of the audience costs.
Yeah, I mean, so people have used this in the past to try and say that they have measured the audience cost. That's and they just use it to refer to sort of the deterministic part of that rather than. So I mean, like in this example, it would be sort of the constant plus the democracy parameter. And so yeah, people have looked at that before, and also
that doesn't really get to your point though, because democracy is observable to everyone, right? It's not the fact that your democracy is not private information.
Yes.
So in order for there to be multiple equilibria, there has to be a private information component, right? And that part is not observable, certainly not to the analyst or the researcher, and also not to the player. But it seems like your model is sort of saying, or what you're saying that you can do with your model is, I can identify which equilibria is being selected, and that is in part contingent on essentially how people are thinking about epsilon. Right? Would that is there any way to use that to identify epsilon?
Yeah. I mean, I have to think more about that, but it seems like it would be. It seems like there should be a way to pull out those residual. That's not something I've not necessarily considered before, but I think that that's possible at least, and might be an interesting avenue for future work in terms of identifying sort of what sort of maybe what kinds of values of the private information needs to take on in order to actually lead to, say, war or something like that. Yeah.
It also might be a little bit of a validity check on the model itself, because if you would think that if everything's working, you shouldn't see widely varying values, right? You shouldn't see audience costs fluctuating massively from year to year or from dyad to dyad. They'll be different to some degree, but they shouldn't be massive differences.
Yeah, I think that's right. And as I think more about it, I think that that might be sort of inherently doable in especially, if we were to move this into more of a Bayesian framework. I think that would allow us to at least back out some of that. Maybe some of that has an interesting parameter, because then we can get some of the underlying kind of like latent variables that go into that final choice node. Yeah, I think that could work.
I mean, I just know that a lot of work. For example, measuring ideology, which is a really something a lot of people have tried to do, right? That work has taken on, that's essentially a lot of the value in that project is measurement, right? It's not just about trying to predict Supreme Court justices' behavior or something. It's ultimately about the measurement. And you might be able to use this in a similar way.
Yeah. Actually, on that point, though, I think it's if we're talking about something like measuring audience costs, then I doubt if you or anyone else is actually interested in that endeavor, that AJPS paper with Mike that I referred to earlier, that's forthcoming, actually is just all about that. Mm-hmm. And so if you want to see some of what we've done on that, then I encourage you to check that out.
Well, we are out of time, so I'd like to thank first Casey for doing this, being our presenter this week. I want to point out that the presentation will be posted to the website shortly after the broadcast if you'd like to share it or to watch it again later. I'd also like to announce that next week the IMC is off for spring break. However, we will be back on Friday, March 23rd, when we will host a talk from Aaron Hartman at the University of California, Los Angeles. Please see our website, www.methods-colloquium.com. To get some more information about this talk. Casey, thanks for being our presenter this week.
Thank you.
And I hope to see everyone in 2 weeks.